Hello everyone. In the previous lecture we learned about the argument principle. And now we are going to see how the argument principle could be used in order to discuss the stability of the closed loop system by referring to the open loop system. Well, to have the Nyquist stability criterion, we will evaluate 1 plus L of S on the contour C1. And if you remember, the contour C1 that we are discussing now, it includes the whole right half plane. So this is our contour C1. It includes the whole right half plane. And we will evaluate 1 plus L of S on that contour. Therefore, we will define Z as P as Z will be the number of zeros of 1 plus L in the right half plane. In the right half plane means that inside the contour C1. And P will be the number of poles of 1 plus L in the right half plane, which is indeed inside C1 again. And then we will apply the argument principle. The argument principle tells us that the clockwise encirclements of the origin in the evaluation of 1 plus L this time on the contour C1 will be equal to N will be equal to Z minus P. So basically up to this point everything is the argument principle. We just have replaced H with 1 plus L of S, and the contour that we have is C1, which includes the whole right half plane. But now we need to see how this could be used in order to determine the stability of the closed loop system. If we check the 1 plus L of S that we have, where for L of S we use the NL over DL, and keep in mind that L of S is the loop transfer function, which is basically GC times GP, the loop transfer function. We will have 1 plus L equal to 1 plus NL over DL, and it could be written in the form of DL plus NL over DL. And now the pose of 1 plus L pose will be obtained by setting DL equal to 0. And you can already see that these are the poles of the L of S, or the open loop. The zeros, on the other hand, are obtained by setting DL plus NL equal to 0. On the other hand, if you remember from the transfer function for the closed loop system that we had, or for the sensitivity functions that we had, T will be equal to L over 1 plus L. If I replace L with NL over DL, 1 plus NL over DL, T will be in the form of N over N plus DL. And you can see now that DL plus NL equal to 0 will give us the poles of the closed loop system. So the poles of 1 plus L will be the poles of open loop system, and the zeros of 1 plus L will be poles of the closed loop system. Okay, so this is important to keep in mind. In other terms, over here, the Z and P will be, Z will be the poles of the closed loop system, on the right half plane, and P will be poles of the open loop system on the right half plane. And therefore, if we have the mapping of 1 plus L over the contour C1, we can determine the value for N, the value for P, which are the unstable open loop poles of the system, should be also easy to find, and based on that we can determine the value for the Z. So here we have it. Z is the number of the unstable poles of the closed loop system. P is the number of unstable poles of the open loop system, so the poles which are on the right half plane. And then we can also take, since obtaining the map of 1 plus L will not be, let's say, straightforward if you want to evaluate it, instead of obtaining 1 plus L, we can obtain the mapping for L of S, which would be easier indeed. And there is a direct relation between these two. So if you assume that on this side we have the map of 1 plus L, if we shift everything towards left by 1, we will get the mapping of L of S. Because the difference is only 1 in terms of the real value. Yeah? So we can easily shift 1 plus L by 1 units towards the left in order to obtain the mapping for L of S. But the important thing here to keep in mind is that instead of finding the encirclement of the point at 0, the point at the origin, this time it will be shifted towards the left by 1 unit, so we need to consider the number of encirclements around the point minus 1. So this is quite important to keep in mind, and over here you see how it is obtained. It's also written here. So if the contour evaluation of 1 plus L encircles the origin, the contour evaluation of L, which now we call it as the Nyquist plot or Nyquist diagram, will encircle the point S equal to minus 1. And here we can summarize the things that we have. We know that N will be equal to Z minus P. N is the net number of clockwise encirclements of the point minus 1 for L of S, evaluated on C1. Z is the number of the unstable poles of the closed loop system. And P is the number of unstable poles of the open loop system or L of S. And now we are ready to formulate the Nyquist criterion. So we have N equal to Z minus P, therefore we can rewrite this in the form of Z equal to N plus P, which we have over here. So Z is equal to N plus P. Z is the number of unstable poles of the closed loop system. It's equal to the N number of clockwise encirclements of the point S equal to minus 1 plus the number of unstable poles of the open loop system or L of S. So Z will be equal to N plus P. Basically, we will draw the Nyquist plot. We will count N. We will check out the value for P, which is easy to obtain. And then based on that, we can say that the closed loop system has Z number of unstable poles. If you want to have the closed loop system stable, Z should be equal to 0. And Z couldn't be a negative value, as we will see later. So Z will be either 0 or a positive integer. It will be the number of the unstable poles of the system. And if you want to have the closed loop system stable, Z should be equal to 0. Or in other words, N should be equal to minus P. P will be a positive value as well because it is the number of the unstable poles of the system. And therefore, in order to have the closed loop system stable, if we have unstable poles for the open loop system, we need to have counterclockwise encirclements of the point minus 1 as the number of the unstable pose of the open loop system. Alright, so I think that's all for this video. In the next videos, we will go through a few examples where you will learn how to draw the Nyquist plot and how to determine the stability of the closed loop system using the Nyquist plot. Thank you for watching and see you in the next video.